Today we shall discuss about the interaction of heavy charged particles with matter. So the ionizing radiations can be broadly classified into charged and uncharged. So in charged particles, again we can classify them into heavy charged particle and light charged particles. So heavy charged particles are like alpha particles, heavy ions, and fission fragments. So these alpha particles, which are very heavy when compared to other charged particles like electrons. So the main mode of energy loss of these alpha particles will be Coulombic interactions. So when these alpha particles travels in a medium, they lose energy by way of Coulombic interactions. Now let us consider a beam of alpha particles interacting with a material medium. So this is the medium, a beam of alpha particles. So if you consider the alpha particles entering this particular medium from left to right, so you will see that they move almost in a straight line, and the ionization intensity increases with the thickness of the material medium, and the intensity of ionization will be maximum at a point which is equal to the range of that alpha particle. So this particular range depends on the energy of the alpha particle and also on the property of the material medium. Now, the most important parameter with which the interaction of heavy charged particle like alpha particle can be described by a parameter called specific ionization. Given by S. So S equal to E by dx. So because the energy decreases with the thickness, so it is normally represented by a negative sign. Now Bethe and Bloch have derived this formula for the specific ionization or the specific energy loss. So d by dx is given by n v. So where n is the number density, it is the number of electrons per unit volume in a material medium, and V is given by this is the relation which is derived by Bethe and Bloch for the specific energy loss of heavy charged particle. So this E is the charge of the electron and Z is the charge of the heavy charged particle, and Z, capital Z, is the atomic number of the material medium, and m0 is the rest mass energy of the electron, and v is the velocity of the charged particle. So beta is nothing but velocity by the velocity of the charged particle by velocity of light. So this is basically the relativistic correction for high energy charged particle. So you will see here d by dx, the specific energy loss, is inversely proportional to the velocity of the charged particle. That means the kinetic energy of the particle. And it directly related to the number density, n. It is the number of electrons per unit volume of the medium. So therefore the d by dx you can say that depends on the property of the charged particles and also on the property of the material medium. So therefore if you see how this d by dx varies as a function of the thickness of the material medium. So we will plot d by dx as a function of x. And let us see how it varies. So initially there will be some amount of energy loss and it gradually increases with the thickness. And at the end you will see the maximum deposition of energy. Okay. So this peak where you have maximum deposition of energy is called the Bragg peak. And this curve which represents the specific energy loss is called the Bragg curve. So therefore what you see here, the Bragg peak, the position of the Bragg peak, basically we expect that if we have alpha particles moving from left to right, all alpha particles having same energy, we expect that they all should stop at some particular point. But you have a distribution at this particular point, not a sharp decrease. So that means the energy deposition of a charged particle is a statistical process, and therefore you expect a distribution at the end. Therefore this is called the energy straddle. So this position of the Bragg peak depending on the energy of the alpha particle. Suppose you have low energy, let us say this corresponds to energy E1 and this corresponds to, let us say, energy E2. So you will have something like this. So here E1 is greater than E2. So therefore by changing the energy of the alpha particle, you will be able to shift the position of the Bragg peak. So for different alpha particles, you will have different Bragg curve. So therefore, this Bragg curves is of practical importance in case of radiation therapy. Now suppose you have a radiation, make use of radiation for the cancer treatment and the tumor is located deeper inside the human system, then you will be able to deliver the dose specifically to that particular target. So by changing the energy of the alpha particle, you will be able to target. So if the position of the tumor is somewhere here, you can fix the position of the Bragg peak at that particular location. If it is somewhere here, then by tuning the energy, you will be able to target the tumor. So this is one of the applications of heavy charged particles in radiation therapy to treat the cancer patients. Now another challenge as far as the energy deposition of the charged particle is concerned, how to find out the range of the particles. So what do you mean by range? Range is the distance traveled by particle before coming to rest. So therefore, if we consider a beam of alpha particles, which are, let us say, traveling from left to right in a material medium, and if you are interested to evaluate the range in that particular medium. So this is the beam of alpha particle. Now you will see that the number of alpha particles remain almost constant with the increasing thickness. Okay, so only when it reaches the range of the alpha particle R, so there will be reduction in the intensity of the alpha particle. So this is the kind of picture you get if you increase the thickness and count the number of particles. Now let us say in terms of percentage, it is 100% of the alpha particle. And let us say this is 50%. So it is very difficult to find out the exact range of the alpha particle even for the monoenergetic alpha particles. So you will have a distribution here at the range. So this is called the range straggling of alpha particles. So here we had the energy straggling. So in case of range, we have range straggling basically because the statistical nature of the energy deposition of alpha particles. So you will see the number of alpha particles almost constant, but though they deposit energy while traversing in the medium. So this is primarily because the alpha particle is very, very heavy when compared to the electrons with which it interacts. So only at the end it loses its energy and it will come to a halt or rest. That is what we call the range of the alpha particle. So practical range is normally defined as we call it as the mean range. So mean range is the thickness of the absorber at which the intensity reduces to 50% of the initial intensity. So this is the mean range. Where the intensity, original intensity, reduces to 50% of the initial value. So another way of evaluating the range is what is called the extrapolation. So you extrapolate the linear portion of the curve and made to cut the x-axis. So this is called Rx. So Rx is called the extrapolated range. Where we extrapolate the linear portion of the curve and made to cut the x-axis. So these are all the ranges which you can determine by experiments. You can also evaluate the range theoretically from the specific energy laws. And R is evaluated as 1 by d by dx. We will evaluate over the entire energy range. Suppose the charged particle has energy E0. So then you have to integrate over the entire range. So because this is minus d by 0 to E0. So over the entire energy range you have to integrate. So you have to mathematically do this. So you know from mathematics that you change this negative sign, you can change the limit. So this will be E0 and this will be 0. So therefore, theoretically you will be able to evaluate the range of the alpha particles from its specific energy laws. Now this range is for a medium in which we consider all the atomic species are same. Now suppose you have a medium in which you have a compound you have more than one atomic species. Then how do we evaluate the range? Now, for a compound, for example, if you consider a medium which consists of more than one species of atoms. In the compound. And that is basically given by Bragg relation. Now, suppose you have two medium, let us say a range of alpha particles is given, one medium is R1, R0 and another medium is R1. Now, this is related to the density of the medium. So, this is rho 1, rho 0 and then the atomic weight. That means these parameters are on the right hand side are constants. Therefore, if you know the range of alpha particles in one particular medium, so you will be able to find out the range in other medium. So this relation is very useful to find out the range of alpha particle in an unknown medium. Now these are the atomic weights of the respective medium and rho 1 and rho 0 are the density of the respective medium. Now if you have a compound in which you have more than one atomic species, then this range in a compound is given by RC is equal to NC by connection. So where RC is the range of the alpha particle in a compound or a heavy charge particle in a compound, NC is the molecular weight, of the compound, and Mi is the atomic weight of the element, and Ri is the range of alpha particle in the element Mi. So therefore you can have n number of species, and if you integrate you will be able to find out the total number of species in a given compound, and using this relation you will be able to find out the range of a charged particle in a compound. So I think we will conclude with this. Hope you enjoy.